Hey everybody, Dr. A here, and in this video we're going to be discussing torsional shear stress in circular shafts. So that's a shaft with a circular cross section. So to get started with this video, you can see I already pre-wrote some of our notes, but you need to, if you're rusty on this or this is the first time going over this material, you need to write all of these notes down in your notebook and be very organized with it, okay? So let's get started. First, we're going to start with saying torque moments, which we typically call T, cause the cross-section of a member to tend to twist. Now, if the term torque moment sounds a little familiar, it should. You've dealt with moments before. Most likely you've dealt with bending moments. And if you remember, a bending moment is a tendency of rotation caused by a force multiplied by its distance, usually the perpendicular distance, away from a desired point. So a torque moment is the same kind of thing, mathematically at least, but physically it is a bit different. A torque moment will cause a member's cross-section to tend to twist, whereas a bending moment tends to cause the length of a member to bend about a certain point, okay? So let's consider a three-dimensional shaft. So I've already written here, let's consider the shaft. And over here I've drawn kind of a three-dimensional figure of a shaft. So back here at point A, we have a fixed connection. That's why you see these little wispy points here. We have a fixed connection at A. And then at point B, the opposite end, it's a free end. So you may call this like a cantilever shaft. So let's make a little note here. This is a 3D shaft. Okay, that's our figure here. And let's say that the free end is subject to this torque moment T here, okay, that I've drawn in red. All right, so that means that this torque moment T is going to cause the length of this shaft to tend to twist within its cross section. So let's define our variables here in red. First, we have T as our torque moment, okay? And this is what we would call an applied torque moment. Now, as I mentioned before, torque moment is a type of moment. So it has units. Remember, this little triple equal sign means has units of force times length, okay? So that would be like kip feet, pound feet, Newton meters, something like that, force times length. In vector form, we can write that as a vector equation, T vector equals R cross F. So if maybe you're thinking from a statics perspective using the cross product, you can write that in vector form like that. In scalar form, you can just take a radial distance multiplied by a force F. Okay, so let's consider, that's how you can express F if you have a force times a radial distance of some sort. So let's consider this shaft figure right here. Consider the shaft's cross section. So if you see this figure right here, this figure is referencing if I pass a cut section at any point in this shaft. Okay, and in this particular shaft, if I make a cut using method of sections anywhere here, it's going to have an internal torque moment T in the cross section. And so when we are looking at a shaft's cross section in 2 dimensions, as we have here, we need to keep in mind a few overlying assumptions. First, we're going to use linear elastic behavior relationships, okay? So for the purposes of this video, we're assuming everything is behaving linear elastically. Next, we're going to say the shaft section will not warp or bulge. That means that the plane of this cross section is not going to deform in or out of the screen at you. It's going to remain planar, okay? And then the third underlying assumption we're going to mention is that radial lines remain linear, but they do rotate in the plane of the cross section. So that means if you have a radial line right here, like I've drawn here, it's coming from the center of the shaft and extending to the edge. Due to this applied torque moment T, this radial line will tend to rotate to a new position. That's what I've drawn here with this dotted line. Now, that angle of rotation is sometimes called the angle of twist. We're not really going to talk about that in this video, but that will be saved for another video, okay? So this is all if you have an applied torque moment. Well, what if you're given some kind of force at the edge of the shaft and you want to calculate this torque moment that we've drawn here. Well, we can make a little note here. We can say we could also have a shaft cross section, and if you have a shaft with radius r and you have an applied force F here at the edge, then this kind of torque moment could be generated just like this T from this one of these relationships here, okay? So that's where we say T is going to be F, R times F, or R cross F, okay? So just letting you know, if you're ever given a force applied at the edge of your shaft, then it's going to cause that cross section to tend to twist, and that F at a perpendicular distance R away from the center is what's generating that torque moment T, okay? So sometimes you see situations like this. Sometimes you see situations where the torque moment is already directly applied, okay? So let's move on. So the next thing we're going to mention is a linear stress distribution will develop in the shaft's cross-section due to that internal torque T. So let's sketch that out. I'm going to sketch the same cross-section out again. Let's see, color coordinate properly. I'm going to go with black here. Okay, so this is still my cross-section of my shaft. Just redrawing it. And again, let's say I've got that same torque moment here, T. All right, so let's say that this shaft has a diameter of D, and let's say that it has a radius of R, okay? So just keeping with our same nomenclature. So when this torque moment is being sustained by this shaft's cross-section, a linear torsional shear stress distribution will develop. And it's going to look something like this. It's going to start at 0 at the center of the shaft, and it's going to extend to, whoops, did not mean to scroll there. It's going to extend to a maximum value at the shaft's edge. So right here at the shaft's edge, we're going to have a tau max, okay? Now, when we say linear shear stress distribution, first, remember shear stress means that you have a stress distribution in the plane of the cross section. So this is parallel to the shaft's cross section in 2 dimensions, okay? Linear refers to the fact that your shear stress is 0 at the centroid, or at the center of the shaft, and it linearly increases in magnitude to the shaft's edge. Okay, so this linear distribution here is a linear increase in the magnitude of tau. Okay, so we're going to say tau max is the maximum torsional, write this down, shear stress at the shaft's edge. Okay, now at an intermediate radial point somewhere in the shaft's cross section, you can still calculate what that shear stress will be. So for example, let's say you're interested in the shear stress maybe right here or right here, wherever, some point not at the edge. That's no problem. What you would consider is a concentric circle inside of your shaft circle, maybe something like this, that has some radial distance, call it rho, okay? And then what you would be calculating, or what you may be interested in calculating, is the shear stress at radial distance rho away from the center of the shaft, okay? And so let's just call that, I'm going to put a little reference arrow here, let's just call that tau, okay? So we're going to say tau is the torsional shear stress at a radial distance rho measured from the shaft's center. Okay, so how do we actually calculate these? How do we calculate tau or tau max? Well, here's how we do it. We're going to say that tau equals T times rho over J. That's our quick handy formula. T is the torque moment, internal torque moment at the point along the shaft you're interested in. So that's our red T right here. Rho is that radial distance. Rho is measured from the center of the shaft to, whatever distance you're interested in that's within the shaft. And then J is something called the polar moment of inertia. So let's write this down. Rho is our radial distance measured from the shaft center. J is what we call the polar moment of inertia of the cross section. Now, if that term moment of inertia sounds familiar, it should. From statics, you probably learned something about Ix and Iy. That's a moment of inertia about a centroidal x-axis or y-axis. Well, the polar moment of inertia is also a type of moment of inertia, but it's the moment of inertia about the longitudinal axis of your member, also sometimes called the pole or the z-axis. So sometimes instead of J, we see it labeled as I sub z. So some textbooks or references, you'll see J, sometimes you see I sub z, but in either case, it's referring to polar moment of inertia, okay? Now, for a lot of common shapes, you have ready-made formulas that you can use to calculate J. So for a circular shaft, we have two common formulas, okay? So we're going to say for solid circles, J is equal to pi d to the fourth over 32, or you could write that as pi times the radius to the fourth over 2, okay? So again, these will both get you the same thing for solid circles. If you just plug in d over 2 for radius and then you raise that 1/2 to the fourth power, you'll pop out a 32 in the denominator. Now, what about for hollow circles? So like pipes, for example. So for hollow, or sometimes called annular circles, we've got J equals pi times d outer to the fourth minus d inner to the fourth all over 32, or you could write that as pi times outer radius to the fourth minus inner radius to the fourth over 2. Okay, so be very careful with what kind of shape you have. And remember, these are both for circular shapes. So you have solid circles or you have a hollow circle, okay? Circles specifically, all right? So, so let's go back to our governing equation. Whenever we are interested in the shear stress at the shaft edge here, then rho is equal to the total radius r, okay? So let's write that down. So when we are at the shaft edge, rho is going to be equal to the total radius r, and tau becomes tau max. And then we're going to say tau max equals, what do you think? Instead of T rho over J, what are we going to have? Well, we'll have T r over J. Okay, and so these are our governing formulas here that you want to definitely make note of. Tau max is T r over J, and an intermediate shear stress value, tau, is equal to T rho over J if you're somewhere in the middle of the cross section, okay? Now, one last comment. We've said that this is a linear distribution. So what do we mean by linear? So let's make a little note here. So this is how this tau formula is linear, okay? Tau, again, general tau is T rho over J. So how about we package this as T over J times rho, okay? Now, rho is a radial distance that we can treat as our independent variable, and then we can treat tau as our dependent variable. So we're going to say this formula has the form of y equals mx. Now that should be familiar to you. This is the form of a linear equation just with a 0 for the y-intercept. So we're going to say where rho is the independent variable like x, tau is the dependent variable like y, and t divided by j is the slope like m. Okay, so that's what we mean by this is a linear stress distribution. So, you know, if I'm going to draw this a little bit bigger so maybe we can see it better. So if we have our circular shaft with a total radius of r, and we've got our torque moment here, then here is our shear stress distribution. In fact, let me move my radius r label up here so it's out of the way. Okay, and again, this is linear right here. So what we're saying is if you treat rho as a like a variable distance right here, and we say that the domain for rho is from 0 to r, then the way you calculate the shear stress at any point tau at a distance rho away from the center is given by this governing equation. Okay, and then again, when rho equals r, you're at tau max. So again, all I'm doing at this point is just kind of showing you that this is just a linear equation. This is a form of a linear equation. It's maybe labeled a little bit differently or new to you, but this isn't rocket science or anything. This is just mechanics of materials, right? So this is just mathematically something you've actually seen before. All right. So that's going to conclude this video. Again, hopefully you wrote all of this down and go back, rewind, and watch this. I know this, if this is new to you, this can be kind of tricky to wrap your mind around, but hopefully this video has been helpful. If so, please hit like and subscribe. Thanks for watching.